Have you ever really stopped to think about your refrigerator? I mean, it just sits there, humming away. But inside that ordinary box is an extraordinary puzzle, a process that seems to break one of the most basic rules of the universe. And here's the puzzle. How on earth does a refrigerator get cold inside when it's sitting in a room that's already warm? It feels completely backwards, you know? It's like trying to get water to flow uphill. It shouldn't work, and yet it does, all day, every day. So what's the secret? And this, right here, is the core of the mystery. We all know how things are supposed to work. Heat always flows from hot to cold. Your coffee gets cold, the ice in your drink melts. It's a one-way street. But a refrigerator, it does the complete opposite. It grabs heat from the cold inside and shoves it out into your warmer kitchen. The key, you'll see, is that one little word, work. It's not magic, it's physics. So, to crack this puzzle, here's our game plan. First, we're going to have to rethink what we mean by heat and energy. Then, we'll get into the really cool part, the heat pump cycle. After that, we'll see just how efficient this thing can be, which is pretty mind-blowing. And finally, we'll land on the big idea. These machines are energy movers, not energy makers. Okay, first things first. Before we can really get how a fridge pulls off its trick, we've got to clear up a couple of common mix-ups about what heat actually is. So for a long time, people thought heat was some kind of invisible liquid called caloric that flowed around. Turns out, that's not right. Heat isn't a thing at all. It's a process. It's just the word we use for energy being transferred from something warmer to something cooler. And that leads us to this idea of thermal energy. Now, this is the total energy of all the little particles jiggling around inside something. And the key here is that it depends on temperature and how much stuff there is, the mass, which leads to this wild fact. A giant cold lake actually contains way more thermal energy than a tiny steaming hot cup of coffee. Kind of blows your mind, right? All right, now that we've got our terms straight, we can finally pull back the curtain on the refrigerator's trick. And it's all thanks to a really elegant process called the heat pump cycle. And here's maybe the best way to think about it. Refrigerators and air conditioners, they're basically just heat engines running in reverse. You know, a car engine burns fuel to create heat, which it turns into the work of moving the car. Well, these devices do the exact opposite. They use work to move heat. And what's really cool is that the heat pump that warms your house in the winter is basically the same machine as your refrigerator or AC. They're just focused on different goals. A heat pump's job is to make the warm place, your house, even warmer. A refrigerator's job is to make the cold place, the inside, even colder. It's the same technology, just pointed in a different direction. So how does this cycle actually work? Well, it's a four-step dance. First, inside your fridge, a super cold liquid refrigerant in the evaporator coils soaks up heat from your leftovers and boils into a gas. Second, that gas gets sucked into the compressor. That's the part that hums. It gets squeezed, and just like pumping up a bike tire, that pressure makes it get really hot. Third, this hot gas flows to the condenser coils on the back of the fridge. Since it's now hotter than your kitchen, it dumps its heat out into the room and cools back down into a liquid. And finally, that liquid shoots through a tiny expansion valve, which causes it to instantly become incredibly cold again, and the whole cycle is ready to repeat. It's all about manipulating pressure to move heat around. Okay, so we know the process is clever, but the next question is obvious. Just how well does it actually work? This brings us to efficiency. Now, for these devices, we don't usually talk about efficiency in percentages. We use a metric called the coefficient of performance, or COP. It's really just a simple ratio. It's the amount of heat you successfully moved, divided by the amount of energy you had to spend to move it. What you got out divided by what you put in. And this, right here, is where things get almost unbelievable. A good heat pump can have a COP of up to 4. Think about what that means. It can deliver 4 times more heat energy than the electrical energy it uses. For every single kilowatt hour of electricity you pay for, you can get 4 kilowatt hours worth of heat pumped into your house. I know what you're thinking. Getting 4 times more energy out than you put in, that sounds impossible. It sounds like you're creating energy out of thin air, which would totally violate the conservation of energy, right? But here's the beautiful solution. No laws are being broken. The heat pump isn't a free energy machine. It's an energy shipping company. You pay for that 1 unit of electricity to run the compressor, but that 1 unit of work gives the system the power to grab 3 more units of free thermal energy that was already sitting in the cold air outside and move it indoors. So 1 plus 3, that gets you the 4 units of heat. The energy was always there. You just paid to have it moved. Now, of course, this can't go on forever. There is a hard limit on performance, known as the Carnot efficiency. And what it tells us is that the efficiency is totally dependent on the temperature difference between the hot place and the cold place. The bigger that temperature gap, the harder the machine has to work, and the less efficient it becomes. And this explains a very real-world problem. You ever wonder why heat pumps have a reputation for not working so well in super cold winters? This is it. When it's freezing outside and you want it to be toasty inside, that's a huge temperature gap. According to the laws of physics, that bigger gap means a lower maximum possible efficiency, which means a lower COP. The pump has to work like crazy just to move a little bit of heat. So let's wrap this all up and get to the big takeaway. After all this, the most important thing to remember is that these amazing devices are energy movers, not energy makers.
So, to put it all together, your fridge doesn't make cold and a heat pump doesn't make heat. They are just incredibly clever machines that use a little bit of work to move a whole lot of existing heat from one place to another. And while the process is so efficient it can feel like magic, it's not. Its performance is and always will be governed by the unbreakable laws of thermodynamics.
And that leaves us with one last massive question to think about. This technology is so much bigger than just keeping our milk from spoiling. If we can move heat this efficiently, pumping it from where we don't want it to where we do, what does that mean for the future of how we heat and cool our entire world? That's a puzzle that's definitely worth solving.